All right, we want to begin one of our first discussions on periodic properties. A periodic property is anything you can tell about an element based solely on its position on the periodic chart. The first periodic table we're going to look at is going to be atomic radius. Okay, so what is atomic radius? Atomic radius is half the distance between two neighboring nuclei of two identical atoms. Remember, our electron cloud, we think of it as a sphere, but it's not really something we can touch, right? But we know where our nuclei are located. So if we have an atom bonded to itself, we say half the distance between those two nuclei is our atomic radius. Chemistry is easy, life is hard, yes? Let's take a look at our periodic table and see what our trends are in terms of the atomic radius size. If we wanted to make predictions on this comparative size of an atom, we would assume that as you go down a group, the atoms are going to get larger. And that is indeed what we see. As you go down a group, your atoms get larger. Why is that? Why do your atoms get larger as you go down a group? Well, it makes sense. As you go down a group, you're adding energy levels. So it makes sense that just as an onion gets larger as you add layers, it makes sense that your atom's going to get larger as you add layers. That trend is very intuitive. What's not intuitive is the trend we see when it comes to atomic size as we move across a period. If we look at a period here, one would think, all right, as we move across a period, we're adding electrons, so our atom should be getting larger, right? Bzz, wrong! Set you up there. As you move across a period, you can see that your atom is actually getting smaller. Why is fluorine, which has 6 more electrons than lithium, so much smaller than lithium? Why is chlorine, which has 6 more electrons than sodium, so much smaller? How do we explain the shrinkage across a period? We can explain this shrinkage by using a concept known as nuclear shielding, or effective nuclear charge. How do we explain the shrinkage of atoms as you move across a period? The easiest way to do that is to relate to something we're all familiar with, Star Trek. The nucleus of the lithium atom is a lot like the Starship Enterprise, with a tractor beam on a Klingon bird of prey. And your Klingon bird of prey is your electron. Lithium has 3 protons. So your tractor beam for your Starship Enterprise is 3 protons strong. You have 3 protons pulling on that electron. Not a very strong tractor beam. What happens as we move to, let's say, carbon? As we move across the period to carbon, carbon has 6 protons in it. The charge on its outermost electron, however, is still 1. So you've got 6 protons. So what's going to happen to that Klingon bird of prey? If we've upped the power of the tractor beam, we've gone, Scotty, I need more power. Whoops, that's Captain Kirk doing a Scottish accent for some odd reason. But anyway, we've upped the power of the tractor beam. So that allows us to pull the Klingon bird of prey closer. Just like when we increase the charge of the nucleus, we've increased the pulling power it has on that outermost electron. Well, what happens if we go from carbon to fluorine? We go from carbon to fluorine. We've gone from a nucleus with 6 protons to a nucleus with 9 protons. So we've upped our tractor beam again. So what's going to happen to that outermost electron? It's going to be pulled even closer. So as we go across a period, the number of protons increases, which means the pulling power of the nucleus increases as well. So as a result of that increased pull of the nucleus, our atoms get smaller. In other words, our radius decreases. You're saying, okay, we buy that, we can see that. As you increase the size of the nucleus, you're increasing its pulling power. So your atoms are getting smaller and smaller because they're drawing those electrons in tighter. But wait a second, Dr. Kelly. If that's true, then shouldn't we be seeing a decrease in atomic size as we go down a period? As we go down a group? After all, as we go down a group, we're increasing the size of our nucleus, right? So how come we're getting larger here as we increase the size of the nucleus, but we're getting smaller this way as we increase the size of the nucleus? You can't have it both ways. Sure you can, unless there's another factor. All right, let's take a look at what happens when we go from fluorine to sodium. We have fluorine here with 9 protons, and it's pulled in this Klingon bird of prey pretty tightly. Got a nice strong tractor beam going. As we go from fluorine to sodium, we're adding not just another proton, but we're adding a layer of electrons. How many core layers of electrons does sodium have? Sodium's in the 3rd period, so it has 2 inner layers. Oh, that color doesn't show up at all. Having trouble with, here we go. Around that sodium nucleus, between the sodium nucleus and that outermost electron, you have the first energy level, and you have the second energy level. What are those 2 energy levels? They're layers of pure negative charge. They act like a force field, and they prevent the Klingon bird of prey from feeling the full effect of that nucleus. So what does that Klingon bird of prey do? Aha! It had to raise the tractor beams because I was firing on them. They had to raise their shields because I was firing on them. That means they had to lower the tractor beam. So I get to escape a little bit. What happens when we go from sodium to potassium? We go from sodium to potassium. We're going from having 11 protons to having 19 protons. So we've really upped that tractor beam when we go from sodium to potassium. However, what have we done? Potassium's in the 4th energy level. So we've added another core layer of electrons. we've added the third energy level. So we have 3 layers of electrons, or 3 force fields, preventing our Klingon bird of prey from feeling the full effects of our tractor beam, so that lets our bird of prey escape even more. I'm out of here. So as you go across a period, the tractor beam increases. And the core layers of electrons stay the same, right? As you go from sodium to chlorine, all the elements in between sodium and chlorine all have 2 core layers of electrons. So your core layer of electrons are staying the same, but you're increasing the tractor beam because you're increasing your number of protons. So your atom just gets smaller. As you move down a group, what happens? As you move down a group, although you're increasing your number of protons, you're also increasing your number of force fields. You're increasing your core layers. Your core layers of electrons are increasing. And as you increase your core layers of electrons, that inhibits the pull of the nucleus. So your nuclear pull actually decreases, allowing your atoms to get larger. Okay. For those of you who aren't fans of Star Trek, and I don't know why you wouldn't be. Oh, by the way, why don't you write down Klingon? Write down Klingon. K-L-I-N-G-O-N-S. Write down Klingon. What we've been talking about is a concept known as electronic shielding and effective nuclear charge. The nucleus has a charge, Z. However, how much of that charge is actually felt by its outer electrons, its Klingon bird of prey, is inhibited or shielded by the core layers of electrons. Therefore, what an electron on the outer level actually feels is known as the effective nuclear charge, or the nuclear charge actually felt by the electron. All right. Okay. You've got the Death Star. You've got the Millennium Falcon, your Electron. Your Death Star is your lithium atom. The lithium atom has a nuclear charge of +3, and it has 1 core layer of electrons. It has completely filled first energy level. The outermost electron exists in the second energy level. So there's only 1 layer of negative charge affecting the pull of the Death Star's tractor beam for the Millennium Falcon. As we go from lithium to fluorine, we've increased the size of our nucleus to a total charge of 9. Fluorine's in the second energy level, so we only have 1 core layer of electrons still. So this force field strength hasn't changed as we go from lithium to fluorine. Our Millennium Falcon, or our electron, it's still in the second energy level. Since we've increased the strength of the tractor beam, but we haven't changed the strength of the resisting force, we've pulled our electron in tighter and made our atom smaller. However, when we go from lithium to sodium, we've increased our tractor beam to a charge of 11. Charge on our nucleus is 11. However, what prevents the outermost electron from feeling the charge of the nucleus is now not one, but two core layers of electrons. So we have two forces resisting the pull of the nucleus. Our Millennium Falcon has two core layers of electrons between it and the nucleus, allowing it to escape farther, right? It actually feels, even though we've upped the pull, even though we've upped the charge of the nucleus, because we've upped the number of core layers of electrons, the amount of charge actually felt by our nucleus has decreased. So we've got the effective charge of the lithium nucleus, we have the effective charge of the fluorine nucleus, and we've got the effective charge, Z there, of the sodium nucleus. The effective charge of the lithium nucleus is less than the effective charge of the fluorine nucleus because there's less protons and the same number of shielding. The effective pull of the sodium nucleus is less than the effective charge of the lithium nucleus because it has two core layers of electrons. So those core layers of electrons are making a huge difference. Just to make sure that we've beat this horse into submission, if we go from sodium to chlorine, we've increased the charge on the nucleus to 17. We've kept our number of force field layers, or our number of core layers of electron, constant at 2 inner layers of electrons. Our outermost electron is still on that third layer. Therefore, compared to sodium, we haven't changed the resistance force. It's still two core layers of electrons, but we've upped the pull of the nucleus. Therefore, the effective charge of chlorine is greater than the effective charge of sodium, which makes chlorine a smaller atom. So we can see a correlation between size and that effective nuclear charge. Alright, so let's compare the effective nuclear charge then, or let's summarize rather what we've been talking about. Compare the effective nuclear charge of sodium, lithium, chlorine, and fluorine. First, let's compare the elements that are in the same group. Lithium and sodium are in the same column, i.e. the same group. Sodium and lithium are in the same group, and then chlorine and fluorine are in the same group. As you go down a group, your number of core layers of electrons increases, and therefore the layers muting the effects of the nucleus has increased. So the effective nuclear charge decreases as you go down a group. So the effective nuclear charge of lithium is going to be greater than the effective nuclear charge of sodium. Then we compare chlorine and fluorine. They're in the same group going down there. So the effective nuclear charge of fluorine, because it's higher up, is going to be greater than the effective nuclear charge of chlorine. All right. These four elements are really, really close together. Because of that, we're going to say that the left-right direction is more important than the up and down direction. In other words, when in conflict, this takes precedence. So the effective nuclear charge of fluorine is greater than the effective nuclear charge of chlorine, which is greater than the effective nuclear charge of lithium, which is greater than the effective nuclear charge of sodium. In other words, those... And we can see this mirrored when we come to the atomic radius. The atomic radius of these four elements is going to be the exact opposite. If we were to list radiuses, we would say that the radius of sodium is larger than the radius of lithium, which is larger than the radius of chlorine, which is larger than the radius of fluorine. And if we look at our data, sure enough, that's exactly what we see. So you could say that there's an inverse relationship between effective nuclear charge and atomic radius. The higher the Z effective, the lower the radius. See, I'm not the only one who likes arrows. Your book likes using arrows when examining this trend as well. Oh, they didn't even put the nuclear in here. Let's go ahead and draw another arrow in here. Another thing to think about is the energy of the electron increases with decreasing attraction to the nucleus, right? Any of you who are in a relationship are aware of relationships dynamics. The less attraction somebody has for you, the less attraction between two people, the more power you have in the relationship. Speaking of warped, why don't you write down Breen? Write down Breen. B-R-E-E-N. Breen. The alien race that appeared in the last season of Star Trek Deep Space Nine. Breen. B-R-E-E-N. Breen. Okay. Here's a graph of atomic number versus atomic radius. And you can see how it displays those trends we were talking about. How in a group, as you go down, radius increases. And you can see a group here. Here's our group 1A elements. And you can see as atomic number increases, our radius does as well. You can even see it for the group 7A elements down here, right? Our halogens, you increase their atomic number and their size increases. You go down that group on the periodic table, their size increases. All right. Let's look at the other trend here. As you go across a row, radius decreases. Sodium and chlorine are in the same row, and you can see going from sodium to chlorine, you decrease. Lithium to fluorine, you decrease. Even from potassium to bromine, you decrease. Notice when we're in period 3 there, we're experiencing the leveling off, so to speak, for those D block elements. Here's another graph. This time, we're looking right across our second period. Right, going from sodium to argon, and you can see as our effective nuclear charge increases, our atomic radius decreases. I'm beating a dead horse at this point. I think you have the idea. Let's take a look at a quick example. List the following in order of increasing atomic radius. When you're doing these type of questions, always take it 2 at a time. First, let's compare arsenic and magnesium. Well, let's see. Magnesium's in period 2, arsenic's in period 3, and then arsenic is much farther over. In left and right conflicts, so we've got 2 conflicting trends, right? The downward direction says that magnesium should be smaller than magnesium should be smaller than arsenic, but the left-right direction says that arsenic should be smaller. Remember, when in conflict, we choose the trend told to us by the left-right. So we're going to say that the radius of arsenic is going to be less than the radius of magnesium, or that's going to be our guess. Then we've got another pair to look at, magnesium and bromine, and once again we have that same conflicting trend. Magnesium's higher up, suggesting it should be smaller, but bromine's farther to the left and right. And because when we're talking conflicting trends here, we're talking a difference of 1 period, we're going to let that left-right thing win out. So we're going to say the radius of magnesium is larger than the radius of bromine. So we know magnesium, it looks like, is our largest. So now we have to differentiate between arsenic and bromine. They're in the same period. Arsenic is to the left of bromine, so arsenic should be the larger radius. So magnesium's larger than both, and arsenic is larger than bromine. So, so what is the order of the radiuses? I still can't do Jeopardy. Why the heck do they have them answering the question anyway? I think that's really stupid. That's it. Beep.